Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory as a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the lecture number 25 on the course Marine Renewable Energy Systems, Analysis, Design and Development. In this we separated the lecture sets in 3 sectors. The major focus is on wave energy converter design and development. We discussed in detail about the analysis, design and deployment difficulties as far as wave energy devices are concerned. We picked up an example study of a floating bean shaped buoyant wave energy converter which is patented to IIT Madras and the research group which I work. We explained you the frequency domain numerical model, then time domain numerical model, both linear and weak nonlinear model systems, and how the experimental studies supplement the data required for finding out the virtual damping of the system has also been demonstrated with a video in the last set of lectures. We subsequently moved to understanding design and development of floating offshore wind energy devices, where we call wind tunnels or wind towers, where we also helped you to understand two different support systems like spar and an offshore triceratops. We compared the results with detailed numerical modeling shown on the screen, and subsequently you will also notice there are videos which is explaining you the behavior of these systems when they are supporting offshore wind turbines. The last lecture now in this sequence, before we move on to further detail on design and development of Suzuka Dolphin devices, which is again an innovative model which will be done subsequently by Dr. Patil. Today in this 25th lecture, we will talk about gyroscopic enabled wave energy converters. Credits to Mr. Kondala Rao, my research team member who has worked on this specific topic, who has also supported me in understanding and explaining and also conducting parallel studies to explain the content of this lecture. Gyroscopic wave energy converter is a very interesting concept which is not new, which has been already used since 2012 at different sectors in the world, but essentially gyroscopic stabilizers are used to control the roll motion on ships. So, now the necessity of this kind of device, the necessity of a gyroscopic stabilizer is what we first understand. Then we will see how I can use this as a wave energy harvest system. Let us say we take a vessel. Let us say this becomes the direction of sail of the vessel. Let us correct this to be on a proper form. Let us do okay. It is a typical vessel whose dimensions are, let us say, L, B and let us say H. Basically, it is a ship. It can be also a vessel, can be a cargo, it can be a catamaran and so on. So, when you mark the CG of the vessel somewhere here and try to mark the axis of this vessel as X, Y and Z, as discussed in the previous set of lectures, this vessel has 6 degrees of freedom, 3 translational, which are surge, sway and heave as along X axis, along Y axis and along Z axis, which are translations. We also have 3 rotational degrees of freedom, which are roll, pitch and yaw, which is about X axis, about Y axis and about Z axis. For our understanding, let us physically interpret these degrees of freedom on the vessel shown on the screen. Let us say the vessel moves along X. So, the vessel is not anchored, it is simply sailing. Okay. So, it is totally free to move on the such direction. What we call the propeller direction. The vessel propels, the vessel moves forward or backward in the such direction. Essentially, the vessel has to move only in pure surge direction, but because of the transcendental wave action on the vessel may also show some movement in the sway direction. The vessel will not ideally move like this, the vessel may move slightly like this. Okay? So, there can be some sway motion also, which is very marginal, but it can be there. Let us mark the water line for our understanding. Let us say this is the sailing level In naval architecture terms, we call this as the plume line. Plume line is the maximum draft the vessel can have. So, this portion will be underwater of the vessel, which we call technically as the draft of the vessel, and the rest will be above water. So, the vessel will sail. Usually you will notice for big vessels of cargo, this plume line will be about 15% of H. That is all. So, it is more stable because the vessel is designed as positive buoyant. So, the vessel will sail automatically, no issue. So, now we have seen that when the vessel is in motion, okay, when the vessel is in motion, surge and sway are automatically happening. When the vessel moves forward or backward, the vessel doesn't move horizontal. The vessel also moves like this. Okay, that is because of wave action. Wave is not horizontal. Wave behaves in this fashion, right? So, therefore, there can be an upward motion or upward forces which is hitting the bottom of the vessel, which will make the vessel to get lifted. Okay, therefore, there will be heave motion also. Okay. So, we call this as slamming. So, there will be slamming force which will hit at the bottom of the vessel. Therefore, when you have an experience of travelling on maybe a Yamaha jetter or even a boat, you will notice that the boat as it sails forward will also move up and down. You must have experienced it. Okay. So, all the three translational degrees of freedom are very much active in a given vessel. Now, let us look into the rotational degrees. The length of the vessel is usually very large compared to the breadth and height. Okay, let us keep it in mind. So, let me put this condition here. The length of the vessel is usually very large compared to breadth and height. I can give an example. If it is a ship, the length will be about 90 meters, the breadth will be about 26 meters and height will be about 5 to 7 meters. So, one can very well see that my argument fits much in this statement. The length is very large. Okay. Since the length is very large, rotating the vessel about this axis, okay, about this is very difficult because the length is too much. Okay. So, what is the rotation about y axis? It is pitch. So, generally vessels would sail in this direction will have no pitch motion. It will be very difficult to rotate the vessel about y axis. Now, on the top of the vessel, if you keep on marking some engine room, some other transcendental elements and other substantial systems which are placed symmetric about this axis, rotation of the vessel about this axis will also be not possible, because if you need to rotate the vessel about z axis, you need to rotate the whole length about this point. Okay, it is very difficult, you need more energy, so you do not have that force coming from the environment. Therefore, yaw motion is also physically not possible. What is quite possible is roll. So, the vessel can roll very easily. Why it can roll easily? Because the breadth of the vessel is comparable to height. Okay, it is comparable to height and the breadth is very less compared to length. Therefore, as the vessel moves forward, you will notice that the vessel also twists. So, roll will be very uncomfortable motion and this will cause nausea to people who are travelling on the vessel. People who are on board, they will be affected by two motions. One is the heave motion, which is in the z axis. Other is the roll motion, which is about the x axis. These two will cause high degree of discomfort for people who are all sailing in this vessel. Therefore, friends, generally people use additional dampers, additional controllers to reduce heave motion and roll motion. Okay? The heave motion and roll motion are undesirable movement which will cause disturbance to the people who are on board. Therefore, generally people, the researchers in ship design and naval architecture will deploy external mechanical devices to control responses of the vessel in the heave motion and in the roll motion. So, when we want to do control of motion in heave, we call this, or we can be achieving this using ballasting and deballasting. This can be achieved by ballasting and deballasting. So, every vessel will be provided with a ballast tank, and this takes care of this motion. Partially it can control, but controlling roll motion is very difficult. Even if you provide a tanker, here and fill this tank with water and allow the tank water to oscillate in the direction opposite to the direction of motion of the vessel, thinking that you will control the motion, we call this application as sloshing design. Okay, sloshing. This can help to control the roll to some extent, but what naval vessels do, what submarines do, what underwater vehicles do is what we are interested in to know. They deploy something called gyroscopic stabilizers. What is a gyroscope? How does it work? How does it look like? How does it work? So, they have been used not yesterday and day for yesterday, right from 1910. Germans and then subsequently Russians and now Koreans, Japanese, Chinese vessels all have gyroscopic stabilizers. So, it is not new. So, they have been deployed, they use ballast tanks, they use sloshing tanks, and they keep on using them very frequently to control the roll and heave displacements of the vessel when the vessel is in motion. But our problem is different. We are using this concept for wave energy harvest. Remember that is what it is. See, the wave energy system designs need not be completely new. This can be a modified version of existing technologies, but with an intelligent perspective to use it for our objective. So, that is what we are deploying in this specific lecture. So, gyroscopic stabilizers are generally used for response control mechanisms, but in this specific case we can use it for or as a wave energy converter, because we can ask me a question, how a response control device can be used as a wave energy harvest system. Very interesting question. Let us put this question for our understanding. How a response control device can be used as wave energy harvest system. Okay, very interesting friends. If I control a response, then the response damping is higher. Do you agree? Damping is controlling the response, is it not? If you have heard my previous set of lectures very carefully, you will notice that all wave energy harvest systems need something called virtual damping. We deploy this into a system called power takeoff systems, okay, which we call PTO. The PTO design will follow these lectures. You will notice how a PTO is designed, what are the types of PTOs available in the commercial market, how can we select and deploy them for our wave energy converter designs. We will discuss about this in the upcoming lectures, but PTO is being used as a damping device because unless you damp the motion, you cannot harvest energy. The same concept here. You damp the motion, you harvest the energy. So, gyroscopic stabilizers are used to control the roll response. It means the roll response is damped. When the roll response is damped, that capture is my energy harvest. So, in general, friends, we are trying to harvest energy by controlling the roll response. In this lecture, we are using a gyroscope stabilizer to achieve this, which is not a novel concept, but using it for wave energy harvest is novel. Okay? So, with this background, let us talk about the objective. We will examine the design and development of a novel wave energy converter harvesting wave energy using gyroscope. So, the wave induced motion of the barge will invoke roll response. That roll response will be controlled by a gyroscope stabilizer, and I will use that mechanism for harvesting wave energy. So, we will explain you through this lecture a numerical analysis done on a barge with the gyroscopic stabilizer, and let us see how we harvested wave energy from this wave induced motion of the barge. Okay. What are the major complications in ocean renewable energy? Let us ask this question so that we understand them very clearly before we start putting a new thought of wave energy harvest on a gyroscopic stabilizer. There are many factors which will contribute to the complications in renewable energy coming from the ocean. The environmental effects, energy transmission phases, we already saw that. I have a device, wave comes in, so absorption power, mechanism, transferred power, which we call, so this is mechanical efficiency, this is electrical efficiency, this is overall efficiency. Okay? So, this is the transmission phase. Then deployment of equipment infrastructure to design them, various factors which are involved in designing these systems, then their maintenance and design life, and the design parameters which are site specific of installation. So, these are some of the major factors which contribute to the complications in design of ocean renewable energy systems in general. Having said this, let us see what solutions the industry looks for. Let us take a catamaran hull which is anchored to the seabed using catenary mooring lines. Catamaran hull is a specific geometric form of a vessel which typically looks like this. Okay? So, to understand the catamaran hull forms, the geometry and the spline lines diagram and the cross sections and designs, you have to look into some NPTEL courses on ship design and naval architecture, which is beyond the scope of this specific course as well as this lecture, friends. So, catamaran hull is a specific example shown on the screen here, which is actually a closed system. There are two phases involved in this. One phase is controlling the motion, the second phase is harvesting the energy from the controlled motion. Okay? To maintain this motion in continuous system, we need mooring lines which will also contribute to this, because if the roll does not happen, no energy harvest is possible. Roll will not happen when the mooring lines will not allow that to happen. So, I should use a slack mooring system. Okay? So, the vessel is free to roll. So, the mooring lines also contribute to the overall design of the industrial solution. All wave energy harvest systems in general, friends, has a very simple design. The design need to be very fundamental and simple. This is a golden word, okay? Please note this. All wave energy converter designs need to be or need to follow a simple basic geometry. The design is a very fundamental approach. Okay. Furthermore, friends, a design which is activated to harvest wave energy should have least effect from the environment. The interface effect from the environment on the device or the wave energy converter should be the least. Industry looks for that kind of solutions. Okay? And therefore, friends, the design is based solely on the C spectrum. What we call here is the design is always site specific. You cannot use a device at Gujarat coast which is designed for Tamil Nadu coast, because the sea conditions, the site specific nature are different between the Tamil Nadu coast and Gujarat coast. So, all wave energy converter designs generally have site specific requirements. So, the industry people look for this kind of specific solutions which are all covered in the specific points as shown in the screen. Having said this, let us talk about the gyroscope concept being used for wave energy harvest. H. Kanki et al. Has already demonstrated successfully 3 types of prototype models, okay, which can generate power by controlling the roll motion. So, one could see the difference between these 3 geometries. I would request you to look into the original paper and the set of series of publications done by Kanki, but I am not focused on that particular explanation at this moment. I want your attention to be drawn towards the geometric shape what people used for this kind of harvest. Look at the type number 1. It is spherical or cylindrical, let us say. Okay? So, it is symmetric about all axes of geometry. So, when you use this kind of device, it generates a minimum capacity. You may say the system is wave direction insensitive, but it will not produce energy because the energy is produced only when there is a good amount of motion. This will have the least response motion in waves. Okay? So, therefore, it is expected to produce less energy, but the positive point about it is less weight. Okay? So, it is a very least weighing system amongst all the 3. Let us go to prototype number 2. So, this is actually, you must have seen a rescue vessel which people use during naval rescue operations. In fact, now people started using this even to rescue people from rainwater. For example, in Bombay, in Kolkata, in Chennai, when there is a flooding happens because of rainwater, people use this kind of rescue vessels. You must have used it even if you do not know swimming. On the low tide surface like Goa or even beach like Miami or even Napoli in Italy, people use this kind of raft. They lie over on this, they will be sailing on the water and they will be enjoying the weather. They take sun bath. So, this raft is modified with the superstructure which works as a stabilizer for this motion. So, now this can also harvest, because this will have a freedom to roll, but you would notice that the roll in this capacity is again lesser compared to the third one, because the length and the breadth are more or less equal. Okay? Therefore, this could produce a capacity of about, let us say, 22 kilowatt power, the generator capacity. Look at the third option, which is a very long vessel whose the breadth is much lesser than the length. This rolls very high. So, as the rolling is more compared to this can harvest more power. So, friends, I am looking for a streamlined body which has got a narrow width and narrow immersion depth compared to the length. Therefore, I invoke more roll on the system. As the roll response goes higher and higher, my harvest possibility of energy is larger. So, amongst all the three options, Kenke showed that this geometric configuration could harvest higher compared to the rest of the two, and it also weighs more compared to the rest of the two. Okay, that is a general idea which has been existing in the literature about using roll motion for harvesting wave energy. Let us come to our argument of gyroscopic principle. This figure shows dynamic modeling and stability analysis of a simple gyroscopic exercise. Gyroscope actually is a ball. It is available in the market. This is called gyro ball. You can just Amazon and see gyro ball is available in the market. It comes with a hand strip. People use this for hand exercise. What they do, when you rotate this like a spring and hold the ball, you will feel that this surface of the ball will start rubbing your skin or the palm of the hand. So, it is very good massager. People use this as a hand massager. Okay. So, how does it happen? See here very interestingly, when the balls rotate, the connections between the central shaft and the outer circumference causes friction. This friction will not allow this outer surface to rotate. In fact, the rotation on the outer surface will be more or less compared to the central shaft. So, this concept is what harnessed here. Along the periphery, we provide rotor and friction balls. So, this friction contact between the shaft and the fixed slot will help us to apply virtual damping to this motion. So, this is the roll motion. Let us say it rolls and this transfers this roll to the central shaft. The central shaft transfers it to the periphery roller. The periphery roller will not roll because there is a friction here. So, now what I am doing, by providing a gyro stabilizer, I am controlling the roll motion, correct? Remember, this can only control rotational degree of freedom. It cannot control heave. It can control only rotational degree of freedom. So, here my option is to control roll motion, that is rotation about x axis. So, if this is my degree of freedom, if this is my x axis, this is roll. Okay. So, I again explain, when the vessel rolls, the vessel, this is fixed to the vessel, this is the vessel geometrically. So, the vessel motion is transferred to this, and this motion through this ball joint transferred to the shaft transfers it to the outer periphery, and outer periphery will not allow this to roll because there is a friction joint here. So, this will keep on moving, and this friction along this rotation periphery will apply damping to the roll degree. So, the roll motion is damped. Okay. So, depending upon how much extent this damping happens, I can design a PTO. The design of PTO will be discussed in the coming lectures, but however, one can design a PTO because if you remember, we have studied the virtual damping of PTO for different frequencies or periods of time, and we have seen what are the factors. We picked up the optimal number For a specific bandwidth of frequency, we designed this virtual PTO for my wave energy systems. Is it not? We did this. So, if I know the roll response control happening in terms of percentage of damping, I can design the PTO from this and use this as a wave energy harvest system. Okay, that is what the gyro principle is. The gyro principle is well explained in this reference tool. So, it actually acts like this. When there is a roll happening about this axis, this roll is transferred to this axis. On the other hand, when the roll happens about this axis, the roll is transferred about this axis. This will make to rotate along the periphery, and along the periphery I have friction ball. The friction ball will not allow this to rotate, therefore damping is initiated. Okay? That is what is happening in this figure as well. So, for your keen interest, you can just go to the market and get a gyro ball and see how does it work. It is a very healthy hand massager. You have to roll the ball, keep it in your palm, and after some time you keep on shaking the hand like this, the ball will rotate automatically. But you have got to initiate the rolling. You have to give an initial rolling, then you do not have to further roll it. If you keep on shaking the hand, the ball will automatically rotate. This is called a gyro ball. It is available in the market. It will not cost you much. It is about I think 1K in Indian rupee. So, just get it and try to feel how the gyro ball works. So, gyro stabilizer is a larger size of the same model. Okay. Having said this, let us clearly now understand in this figure how this ANSYS model is used to represent this. Remember friends, ANSYS does not have a ready-made tool of gyro stabilizer. You have got to modify and use additional tools to make this model. Okay. So, this again a patented material to my research team. So, if you want to really plan for any technology transfer of using this for energy harvest, please contact me and we will execute this through the energy research cluster what we have at IIT Gandhinagar as a research project which we can help you in developing the know-how, and we will also collaboratively conduct research on applying this in a real technology transfer in the field. So, let us see how this model was done. So, this is a sphere available as a ready-made box in ANSYS mechanical. So, we have a shaft. So, the rotation is offered to this ball in terms of angular velocity, and the ball is now made to rotate about this. Okay, that is what we are doing, about this. But it is not going to be free. It rotates between the vent where this friction ball moves. So, this friction ball will offer resistance to this motion, correct? And that is how we apply damping. So, when this model was attempted in ANSYS study by Kondal Rao and myself in the research team, for a specific diameter of the rotor, for a given mass of the gyro ball, we could achieve these statistics of moments of inertia and the gear ratio for the design. One can also see the RPM at which this gyro ball rotates. There is a very interesting animation which we can show you this, but unfortunately the animation is at this moment not running, but we will give a link for this animation in the SwayamPrabha website, still you can look at it. Now, let us look at the roll of the vessel and the rotor RPM. How are they matching? Look at the roll of the vessel. The roll of the vessel is more or less uniform, okay, more or less uniform. It varies from minus 40 to plus 40. So, as a mean this is about 40. It is a fairly good amount of roll in terms of degrees friends, it is a good amount of roll. We have designed the system, we have chosen a barge in such a manner that the roll will be extremely large, okay, so that we can harness energy. Now, when I apply when I start understanding the rotor RPM which is required to control this roll, starting from 0 to 200. The RPM required to control this roll or to activate this roll, vice versa, is about 250, which is a conventional motor available in the market. Okay, the conventional motor can get, in fact, you have motors which are about 1000 RPM as well. So 250 RPM for a scaled model is available in the market readily. So that's the RPM required for the rotor, which is attempted and achieved directly from ANSYS. Once this is done, then we want to understand the response of the float. Let us say we have a barge which is designed and modeled as a simple block. Wave is passed, it is anchored with catenary mooring on the seabed, and ANSYS Aqua is run on this, and we can get response analysis as you see here. When you look at the roll motion, okay, let us look at this. Let us look at this. So, we have chosen a barge of length 25 meters, breadth 25 meters and depth 13 meters. We are looking for a more or less a square barge. Okay. The roll varies from minus to plus 30, which is fairly a good amount. It is obtained from ANSYS result. The ANSYS was subjected to wave height and wave period of 2 meter and 7.1 seconds model. Under the beam C condition, the raw roll response amplitude operator is what you see here. At a specific period between 7 to 9 approximately in seconds, the roll response was maximum. Okay? Rest of the time it is not. So, you have to tune the damper or the PTO to harness at this particular frequency range. This is not new only for this device. Even in wave energy converter system designs, the bandwidth of operation should be chosen. We have done that. Okay. So, you see the barge detail and the responses of the barge. Then now we install the gyroscopic stabilizer to the barge in the ANSYS model. Okay, you can see the model here, which is virtually taken as a screenshot, which is connected to the barge with the spindle and the pin arrangement. So, the stabilizer is installed inside the barge with the pin and stabilizing agents. Now, let us see the roll motion after coupling of the gyroscopic stabilizer. So, one can see starting from 0 to 200 seconds simulation run at a specific frequency or the period alone, the rotation goes to maximum. Okay. Rest of the time the rotation is controlled. So, it is this band for which I must design the PTO to harness the energy from the barge. Okay. So, this is the simple animation which will explain the contact position of the barge for entire 800 seconds. You will notice that from the result that the contact position remains almost in the mean position. It does not move much. Okay. So, a catamaran model fitted with the gyroscopic wave energy converter is what you see on the screen. So, these are the ballast tanks which are required to improve the stability of the catamaran model, and there is a hinge, there is a gyro assembly provided at the center between connected to this shaft, and the hinges will help us to allow to transfer the motion from the barge to the spindle. Friends, here is the difference. Generally, gyro assembly is used to control the motion of the vessel, but here we are allowing the vessel to move, rotate or roll and that motion is transferred through the hinge to this shaft. And once the motion is transferred to the shaft, this gets connected to the gyrostabilizer automatically, and from here we harvest power. Okay. So, if we look at the results of hydrostatic of the catamaran hull, the results are shown, hydrostatics are shown on the screen. You will notice that the raw response is maximum at a specific range which we earlier shown you, rest of the time it is not active. If you look at the simulation analysis, the wave elevation is a regular wave taken for the input. The roll response in a coupled motion is controlled, okay, it is controlled. So, this control is a virtual damping applied to the system where I am going to harness energy from this PTO. So, now the gyroscopic stabilizer acts, the gyroscopic stabilizer acts as a virtual damper. Okay. The virtual damper is PTO for my design. So, this is able to control the response nicely in roll degree. Uncontrolled is blue, control is black. You can see it is controlling. Okay. Look at the angular velocity of the rotor, that is also controlled compared to uncontrolled. If you look at the angular acceleration, though it is chaotic, but it is still controlled compared to uncontrolled. Okay. So, the gyro stabilizer is connected to this shaft is connected to the hinge of the catamaran. As the catamaran rolls, the motion is transferred to this hinge and the shaft is connected to the gyro stabilizer harnessed the wave energy because it acts as a virtual PTO. That is the concept here, friends. Okay. So, in the summary of this lecture, we have discussed an innovative concept how a gyroscopic precision device can be used to extract wave energy. The aerodynamic coupling between the wave induced motion of the barge and the gyroscopic control in the roll motion is demonstrated using ANSYS model. The transition from the lab scale to full scale model can be achieved by using a realistic rotor response. What we have used is a scaled rotor response. So, one can use a realistic response. So, starting from rotor response speed about 200 RPM, about 21-degree roll motion can be controlled. So, that is the scale of operation what we have. For 21-degree control, you need 200 RPM motor. So, from this you can make out in a real sea state and real condition of a barge, what would be the RPM required for the gyroscope stabilizer. So, one can design the PTO using gyroscope stabilizer, fix it on a barge, connect it with a spindle and shaft and try to use energy harvest for the system. So, friends, we come to the end of this lecture where we demonstrated the application of a gyroscopic controller which is used for roll response control in large barges, which can be in turn used as a wave energy harvest system design. So, the only gray area what we have now, as I understand, is how to design mechanically a power takeoff system. My book on wave energy converters, co-authored by Faisal Khan of Texas A&M USA and Rosby Abbasi of Macquarie University Australia, will help you to understand the design of PTOs as well. So, this is published by Elsevier. Please look at this particular book for more details which I showed you in the beginning lectures of the reference material. And for industrial partners listening to these lectures, you are most welcome to contact me at IIT Gandhinagar for technology transfer as well as research initiated projects to the energy cluster at IIT Gandhinagar. Stay connected, friends. Thank you for listening to this lecture. Namaste.